So are there any lingering questions from Monday or Wednesday before we get started? Yeah.
What would you say the importance of like understanding the different representations, alternative representations of the tape?
Not super important. It's a side topic, a spur on the highway of our material. It's good to realize that this, two-way infinite tape, there are other ways we could have achieved the same result. That's pretty much it. Yeah, it's not a major topic. It won't go anywhere at all. But just a fact to know as we start Turing machines.
Do you think about that on the exam?
Yeah, I mean, it might be important to realize what things are also equivalent to a Turing machine. I mean, a single stack's not enough, two stacks is. Single or double-ended, multiple tapes, that these are achieve the same goal is the only real point of those. Yeah. Good question. Okay, so here we go. In block, whatever block we're in, block 3, our machines are Turing machines, and we've seen the special machines, total Turing machines, which don't loop. They only accept and reject, they don't loop. We're going to introduce one more set of terms today to complete some things off, and we'll kind of use each of these terms applies to a certain context, and I just want to make sure we're clear on all of them. Just quick warm up. Okay, what kind of set is accepted by a total Turing machine? Recursive. A set accepted by a Turing machine, plain old Turing machine, RE, recursively enumerable. Great. We also have this kind of third thing. If the complement's accepted by a regular Turing machine, then it's called co-RE. Okay, and make sure you're careful with those. By the way, there's no term for complement being accepted by a Turing machine, by a total Turing machine, because if a set's recursive, so is its complements. There's nothing special there. But this fact about recursively enumerable sets being accepted by Turing machines, maybe the complement isn't, means we need a name for those when they are. Our answers to a question, is this string in the set, right? What can you get in a finite number of sets for a recursive set? I give you a string. What answers, yes and no, can you get for a given string in a recursive set after a finite number of steps? You feed the string in the machine, it runs, it can't loop. So you'll get a yes, or whether the answer is yes or no, a total Turing machine will give that answer in a finite number of steps. These are the fully answerable questions by a Turing machine, right? If it's a total Turing machine, it won't loop. You can get the yes answers in a finite number of steps and the no answers. Crucially for a Turing machine, if you're asking whether a string is in a recursively enumerable set and just have a Turing machine as your tool, which answer can you guaranteed get in a finite number of steps? The yeses, the accepts you can get at finite number of steps. The no's might be rejects, finite number of steps, or loops. Okay, so this is the reason recursive sets are kind of better or simpler than recursively enumerable sets. In one case, you can get yes and no answer to finite number of steps. For only RE sets, you can get only the yes answers to finite number of steps. Maybe you can get the no's to finite number of steps, maybe you can't. Big difference. And of course, for a co-RE set, you can kind of get the no answers to finite number of steps, maybe not the yeses. The final bit of terminology, someone already asked about this after the other class, is this term of decidability. Don't forget that when we talked about sets of strings, in week 1, we used sets of strings to represent the yes answers to some problem or question, a yes-no question, okay? There's another set of terms that we apply to problems, okay? Questions, you might ask, yes-no questions, okay? So I want to make sure we have both sets of terms on the same page so we have them lined up. There's a corresponding term for each of these sets. If you think about it, instead of a set of strings, as a question you might ask, which is maybe what we were originally interested in, okay? And you'll hear these terms used in the literature. So for a recursive set, a set for which the yes answers, you can get yes and no answers in a finite number of steps, are going to be called decidable problems. And this should make some sense. These terms may feel better to you than these recursively enumerable RE, co-RE stuff, right? Decidable means that question, I can get a yes or a no answer in a finite number of steps every single time. The question is a given string in that set. Pulling back, if you hadn't expressed the problem in terms of sets of strings, and you're thinking about the problem itself, decidable is the word you'd use. So it's the same concept applied in different contexts. Talking about the set, it's recursive. Talk about the problem, decidable means yeses and nos you can always get in a finite number of steps. The good news is the recursively enumerable, which doesn't kind of sound like half of recursive, turns into, whoops. Sorry, I've already said this. Oh, by the way, quick remark. Undecidable, I hope this is obvious, means not decidable. Okay? It could be either of the other two, though. Okay, same way, by the way, to say a set's not recursive, it could still be RE or co-RE, just not both, or neither. Okay, so to say not decidable is a very broad statement. The two special cases we've got, you might kind of like. The yes half of decidable is called semi-decidable, and now that halfway kind of fills in with the semi. And you can probably guess what the third term is. Co-semi-decidable. I apologize, still a lot of prefixes and stuff. But this might feel better. Decidable problems are ones you can answer yes and no by some algorithm in a finite number of steps, a Turing machine. Semi-decidable problems, you can always get a yes, but maybe not a no in a finite number of steps. Co-semi-decidable problems, you can get the no's, but maybe not the yes in a finite number of steps. There is nothing but vocab here, yes.
First bullet point.
Yes.
A problem is undecidable means that instead of yes answer is not recursive, though it could still be RE or co-RE.
Yeah.
Why would it be undecidable and not like semi-decidable?
It could, so undecidable includes some semi-decidable problems.
Oh, okay.
And some co-semi-decidable problems and some that are neither. In the same way, non-recursive sets could be RE or co-RE, but not both.
I see.
Yes.
Awesome.
Great. See if those work later. Okay, so just some terminology, yes. Yes, oh, two of you, okay. Yeah, I don't know who was first. Oh, boy, very generous, okay.
Just to like frame it all,
Yeah.
basically any problem we can think of that isn't like weird and meta, probably decidable.
Probably. If you can think of a way to answer it, then yeah, it's probably decidable. Yeah, you're gonna have to work hard to get sets that aren't recursive, and correspondingly, the corresponding problems, you have to work hard to get non-decidable problems. That's true, yeah.
Yeah, but again, it's kind of goes back to my previous question last class, and I know we're going to answer it later, but what makes us know that, like, for example, that this is a yes or this is like an unanswer, like a semi-decide?
Oh, we don't. We don't. No, so at this point, I'm not sure if I can get your question right. Is the question, given a machine, how do we know if it's is going to loop or not?
On a particular string or at all or anything? Like we don't...
Hard problem, no. In theory, each problem, like any given problem you phrase, any given set you say, either there is a total Turing machine or there isn't. Theoretically, there's only two possibilities, it's decidable or not. How you would figure out if it's decidable is a totally different question. So the process of determining whether a problem is decidable is we're not talking about yet. We'll find ways to show a problem's decidable. We'll have ways of showing a set's not decidable or a problem's not decidable. Showing this is a different thing than theoretically every problem is decidable, semi-decidable but not co-semi-decidable but not semi-decidable, or neither. But it's only theoretical at this point, absolutely. We do not have a way to determine this yet. Yeah. In fact, we have to work hard to prove that there are even sets that aren't recursive. We will do that on Monday, and it's the halting problem. The halting problem, so we're going to approach it from that side. This could be a bit of machinery to set up first. So here are, I'll hand out the handout here. There are some little questions to fill in. Honestly, I wouldn't fill these in now. I'd fill them in later because right now the whole sheet's in front of you. You just saw this. See if you remember this later, right? So I said this very, very briefly, and I'll just point at it here, and we're going to talk it through just a little bit. Right now in the class is we're going to make a huge jump from states and transitions and little diagrams for Turing machines up to how you should really think of a Turing machine. And maybe you should have a bit of a schizophrenic view of Turing machines. On the one hand, they really do have states and transitions and accept state and reject state, etc. On the other hand, you can take this point of view of how powerful they are. Okay? you could simulate any of your laptops with a finite number of states. And that's the comment I want to make, okay? You could emulate your laptop with a Turing machine. Now, this is completely infeasible in real life, but theoretically you could do this, right? You could say the total number of bits in your machine. This includes your memory, your registers, your cache, all the bits that can be 0 or 1 in your machine, number them all, okay? Some number of billion probably for most of your machines, probably for all of your machines, right? Make 2 to the n states. Every single bit in your machine is either 0 or 1. Take all possible combinations of how the bits could be. Those are these literal states your machine could be in. That's 2 to the billions of powers. That's a ludicrously large but finite number, okay? That could represent, by the state alone, any given situation your computer finds itself in based on what all the bits in the machine are saying, yet it was 0 or 1. Okay, that's possible. The start state might be after booting up what your machine's doing, what all the bits look like, just snapshot all the bits in your machine. This is only theoretical. And by the way, I'm just trying to get you through a plausible argument to the fact that a Turing machine can do at least as well as your machine. There's a lot of things you'd have to check, but this is the big picture idea. The transitions might transition according to whether you press a symbol on the keyboard. That's your input set, right? To the new state of how all the bits in your machine are, okay? And you might, whatever program you're trying to run in Python or otherwise, the configuration of all the bits in your machine when it gets to that part that says return true is going to be your accept state. And the configuration of all the bits when the thing says return false is going to be the reject state. Okay? This is at least plausible, right? The only thing that a Turing machine has that your machine doesn't, via this, is that your machine has a finite number of bits available. I think this came up last class through one question. Technically speaking, it can't store an arbitrary amount of information. It's going to be limited by how many bits of memory it has. The Turing machine has this tape that's infinitely long. The one thing a Turing machine has in your laptop is an infinite amount of storage, okay? Between your memory and even your disk drive or any USB drives you plug in, you only have a finite number of bits of storage. A Turing machine has an infinite amount of storage. That is the one thing it has on your laptop. In every other sense, though, a Turing machine is much like your laptop. Question? Like you're poised for a question. No.
This is kind of dumb, but would you have to internalize any I/O of your computer into the machine also?
I mean,
so
this is
every single thing in the world would have to go into the.
Yeah, I mean, this is an overview simplified model to make this plausible. Because I really am going to ask you to have kind of a two-pronged view of a Turing machine. On the one hand, this is what it is. On the other hand, brushing all that away, what can it really do? And the answer is everything your laptop can do and a little bit more because of infinite memory. Okay? You could kind of take this model of your computer with a bit configuration, like all the bit configurations are the states, and give it kind of an external device for swap space. Someone mentioned swap space before. You could use, say, the left half of your tape as swap space. Like an infinite size USB drive. And, at least plausibly, you then would have infinite storage in your laptop. If you had an infinite storage thing plugged into it, that thing plugged into the left side of your tape, you could put any symbol you want there for as many symbols as you like. Okay? All of this is just to get us to one thought, that a Turing machine effectively can do what your laptop can do, more or less, with the additional fact that it has infinite storage. If your laptop had infinite memory, it would effectively be a Turing machine. Okay? The big thing I need you to get, and we're going to run with this a bit more on Monday, because this is phase 1, is that you can think of a Turing machine in the old sense, and here's where I'm going to be mixing my metaphors. On the one hand, a Turing machine has states and transitions. On the other hand, it acts like your laptop. Okay? Take a Turing machine, think of it in the first sense. There's a finite number of states, some transitions, some accept states, reject states. You can encode that into all that information. Here's how many states there are, here's what the transitions are on, here's where they go to, etc. You could just record all this information into a string. Okay? Here is the thought exercise for today. There's one thought exercise and all the consequences of it. If we encoded a Turing machine into a string of zeros and ones, by the way, any file on your computer is technically a bunch of zeros and ones. Every byte is 8 bits, right? We could think of having something called a universal Turing machine. And this should feel like a black box at first. It's a Turing machine that has a program built into it that can take an encoding of another Turing machine and load it and kind of run it. Okay, and this is kind of the picture I want you to have. This might be on the flip side of your page. Okay? Our topic for today is universal Turing machines. On the one hand, a Turing machine has states and transitions. You could encode it into some data, just storing what the states and transitions are. That string could be read in by a UTM that runs a program to reconstruct it in its memory and be able to run it. Okay? If this feels uncomfortable, I want to try and make it more comfortable in just a second. At least what we're trying to do, and I hope you'll see that you already understand how this works once we get to the end of the next slide, what we're trying to do is have a Turing machine that can run another Turing machine inside of it. Okay, that's the idea. The Turing machine you run inside will be encoded into some string to give all the relevant information. Reading this new Turing machine, this other program, reads that string and reconstructs what the Turing machine should have been, and then can try and run it. Here we go. What should a UTM be able to do? And these are important. And if any of these come up and you're concerned, we should talk about them. But by the end of this slide, my hope is you'll understand what I'm talking about here. Things a UTM should be able to do. It should be able to take a Turing machine encoded into a string, just describing all the states, load that into its memory. Okay? Turing machines, computation machines, enumeration machines, whatever. Along the way, if I give it a string that's an invalid encoding, doesn't encode a Turing machine, it should be able to recognize that, error checking. Okay, so if I give it a string that encodes a Turing machine in some way, it's going to be able to load it up in its memory and think about running it. If I give it a string that doesn't encode a Turing machine, it should be able to say, hey, that's not a Turing machine, right? It should be able to run the Turing machine that it loads in. Okay, and this should feel abstract right now. We're going to look at this list again after we've said what it really means. Okay? In particular, it can run that machine in lots of different ways. It could load a machine in and run it on an input string just one step at a time. Or it could run just just press the play button and keep on running and running and running. It could run the machine either one step at a time, some number of steps at a time, or just run it until it finishes. Okay? A slight danger, if this UTM is loading a Turing machine in, and you say run that Turing machine, and that Turing machine loops, UTM is also going to loop. It's just going to let it run and nothing's going to happen. Okay? It should be able to read the answer that the Turing machine gave you. If it accepts, it can use the fact the machine accepted somewhere else in your program. If it rejects, you can do that. Because it's storing the Turing machine and its tape, it should also be able to examine the tape. While the program runs or after it finishes, it's kind of got an overview of the entire Turing machine as it runs in memory. It can decide how it wants to run it, and it can get the answer, accept or reject. It can also examine what's on the tape while it's running or afterwards. It's got total control over this little Turing machine it's running. It could even load in a Turing machine and maybe swap the accept or reject states, or get rid of some transition or change the machine in some way. It can edit the Turing machine it's loaded. Okay? Once it's edited the machine, it could re-encode it into a new string. Now, this is a bunch of stuff in theory, right? The reason I wanted you to play with these animations are to build the right concept in your head. You've already seen this. Every time you've gone on your laptop, assuming you have at some point in the semester, and loaded up a Turing machine, or maybe you just loaded up a DFA or NFA or NPDA. The thing you're doing on that website is exactly what a UTM is supposed to be able to do. Now, the only difference is the stupid programs in JavaScript are not very fast or powerful, and your machine has limited memory. But more or less, every Turing machine that I gave you a link to is on the server, stored as some string encoding all the information. That JavaScript code decodes that information and builds a Turing machine out of it. It can load a Turing machine out of a file, given a string. It can build a Turing machine from a save file. Okay? It's not very good at this, it'll probably just crash, but it could have had good error checking and say, oh, that string's not a valid Turing machine. The simple fact is, we're only getting these from saving Turing machines, so it's never going to have that happen. I have, at least in class, loaded a Turing machine and just entered an input string and pressed space a few times to run it. I could run it for as many steps as I wanted to. I could also, in theory, just auto tap the space bar forever. Run it until it quits. I could look at the tape as I'm running, or after it finishes. I could see whether the thing said accept or reject in the end. Right? I could even go back to edit mode and change the machine and then resave it. So the point I want to make is this. Any amount of time you play with the animations, the Turing machine animation are pretty much just like the other ones. All of these things we've seen a UTM supposed to do, you've already seen this, the substitute version of it. You've seen this idea already played out. So my point is this. The topic of universal Turing machines. Theoretically, they can do all these things. But you've seen the finite version of a universal Turing machine. All those things are what you've been doing with your animations. You can plug in a string, you can run it, you can run it for a few steps, you can run it until it stops. All of these things you could do on the website. I just want to make sure you realize that's all we're saying we can do in theory. Okay, those things. So before I put this down, I want to make sure any questions come up about this. If it sounded tough and why that's totally theoretical and why I should be able to do this, the whole point is you've seen it. That web page, I mean, here's an example, right? This is the save file for that. Is this one? Yeah, this is literally a text file that saves that Turing machine. This is the file that would be loaded up to get this. It has encoded into ASCII a bunch of bits, all the states and transitions and stuff. You've literally been using a substitute universal Turing machine every time a universal Turing machine. Your laptop is the universal Turing machine. It loads a little Turing machine inside and runs it. Is that okay? I mean, if that's really okay, you've gotten through the hardest part of today.
And how exactly would the meta, like the upper Turing machine, simulates the UTM simulates the moving of the like the reading state inside of the
Yeah, somewhere it has a variable that says where on the tape the head read write head is, just like the animation does. It's storing in memory what all the contents on the tape are, just like the animation does. This is its own little, on the UTM, there's a program that does what this website does, what this JavaScript code does.
Okay. And it has it takes into consideration every possible state that the
Yeah, so every single state of the Turing machine's encoded here in some way. And when it loads it has the entire Turing machine in its memory. And it's able to do all these things that you'd like to, all the things you'd like to be able to do. It should be durable enough to be thrown and not be killed. We'll see. So when I kind of begged you to at least play with the animations a little bit, this is really the day why I want you to see that. We'll talk about this a bit more on Monday as well, but this is phase one. Okay? A string encodes the information about a Turing machine. A UTM can load that string in, process it to see what Turing machine you're talking about, what the states are, and it can do all the stuff the animation can. Yes?
So I'm just trying to connect it to the idea of really old computers with, so in that case, this graph of the Turing machine is literally encoded in the hardware of the computer. And then the tape was the,
Oh, geez.
I'm trying to figure out what of that, what is defining the mechanism of the Turing machine, and is the tape just equivalent to the tape in this? where that's the only part that's encoded and changed?
school machines.
Yeah.
In the old school machines, the Turing machine was the actual machine you ran, and it had a tape for memory.
So then is the jump to like a real, like something we think of as a real computer, encoding one Turing machine physically that accepts some like machine code?
Basically, yeah. So we're working one level forward from that. And by the way, was it this class where von Neumann came up? No, it was an independent study I'm doing. So John von Neumann came with this brilliant idea that the memory for a computer and the storage for a computer, the programs and the data could be stored in the same place. Maybe that was before the tapes. The tapes probably had the programs too. So your modern machine, where you have this massive amount of memory and not just a tape where you can load things in and store them and do stuff with them, is really the model we're talking about. I don't think this analogy doesn't work as well until the modern age. So I think this is a harder concept possibly to grasp until you had literally an animation you could play with of Turing machines. That should make completely real to you all of these things. Okay? So on the one hand, Turing machines just states and transitions and stuff. On the other hand, it's kind of your laptop plus infinite memory. A Turing machine, your laptop, is able to load in any other Turing machine, states and transitions, and do stuff with it. A Turing machine running a Turing machine, this universal Turing machine, by loading a string encoded Turing machine into it, can kind of simulate any Turing machine. This single Turing machine, just load in the correct string, and you've got another Turing machine to run. Load in a different string, you've got a different Turing machine to run. This universal Turing machine is able to run effectively any Turing machine it's given, as long as you encode it in the right way. There's a lot of details there, like how is this encoded? Oh, it's garbage encoding. But you could just somehow, it could have been like, there are blah states, there are blah transitions. Here's the first state, here's the start state, here's the accept state. Somehow or other, it's just compressed a little bit here. Okay. This is the thing to have in your head about that entire list of UTM stuff. I've already said it. There it is in print. It's on your sheet. I think it might be on your sheet. A UTM can do anything you can do with code or systematic use of our Turing machine animation. That should be your mental model for how universal Turing machines work, and it won't be incorrect. This is the correct thought process for universal Turing machines. Just like the animation you've seen, but you never run out of memory. It's going to be important in a second. All right. So here's the interesting thing. This notion of this is the second half of class today. We're just going to go through some thought exercises on things a universal Turing machine allows us to justify. Things that we kind of thought should be true, but we didn't have the mechanism to justify them. A universal Turing machine does this. And here's the thing you need to remember about universal Turing machines, right? They're able to load in a Turing machine, and you can actually run it on multiple inputs if you wanted to. Okay? Now, the simple thing you could do in a UTM, with the animation, say, is load a Turing machine up, enter an input string, and just run it steps until it terminates. The issue with doing so is if that Turing machine you loaded loops, you will loop forever and never get an accept or reject. You could try and run the machine until it accepts or rejects, but you might never finish. I'm pressing the space bar, by the way. Just keep on going forever. If you, in a simple-minded fashion, load in a Turing machine and run it on an input string, if it loops, you loop. But we have more control than that, and that's the crucial fact about a UTM that lets us do a lot more with it. Okay? The fact that we're able to run a Turing machine for 1 step or 5 steps or 10 steps, the fact that we can run a machine just for a few steps and not, as a Turing machine runs in our classical sense, you put a machine in, you put a string in, the machine runs, maybe it halts, maybe it doesn't. Even when the machine you loaded doesn't halt, you're able to have the control to just run it for a few steps and check what's going on. Okay? So, for instance, you could run the same machine or even 2 machines on 2 different input strings. You can run 2 machines at once on a UTM. The equivalent on your laptop is open up 2 windows and put an input string in one, put an input string in the other. There's a slight issue, and time sharing is the big concept here. The wrong thing to do would be to load one machine and run it till it terminates, and then load the other machine and run until it terminates. What's the problem? If the first one loops, you're never going to get to the second one. Time sharing is the most simple-minded thing. Don't let the term, not all the stuff in this class is hard. This is not one of the hard ones. Time sharing allows you to run 2 Turing machines, or 10 or 1,000, at the same time without worrying about loops. What would you do? I could load 2 Turing machines on an input string. I could run the first one for one step, and the second one for one step. And the first one for a second step, and the third one for a second one for a second step. Run the first one for a third step, the second one for a third step, etc. If I do this, I can actually effectively simultaneously run 2 Turing machines, but each one step at a time, alternating. And even if one loops, I will still get through all of them. If one of them loops and the other one stops, well, then I'll at least get the fact that that one terminated and get a result. If both of them loop, I'll just keep on looping, whatever. But one machine's looping can't screw up you running the other machine if you alternate your space bars, so to speak. Okay? I hope that's an obvious fact. Okay, so key fact about universal Turing machine, just like your laptop, you don't have to load just one machine. You can make several windows, and as long as you go in sequence and do one step at a time, loops in one window won't affect the other windows. Clear enough? You look a little bit dismayed. Accepting? If I gave you 2 Turing machines, and I said, run that Turing machine on this string and on this string, you could on your laptop load it up twice, enter the input strings, and go click over here to space, click over here to space. You could do this on your laptop, and that's all I'm trying to make you realize. A UTM can do everything your laptop can do. Okay, this is useful because I can now run 2 Turing machines or run a Turing machine on 2 different strings without worrying about one of them looping. That's actually really important. There we go. This is curious. Remember, your UTM has infinite memory. You could run a Turing machine on an infinite number of input strings the same way, well, more or less the same way. Second thing you should realize, you can do it if you're even more careful. You could run a Turing machine or several Turing machines on an infinite number of strings on all of sigma star, if you're careful about how you do it. There is one hiccup here. You can only run a UTM on a finite number of machines. Why is that? At a time.
Because if you have to step an infinite number of machines, you never get back to the you can never really.
Well, that issue will solve. That would be the same problem if you had one machine running an infinite number of strings. There's a subtle fact here that I'm not going to make a big point about, but realize one thing UTMs can't do. To load in an infinite number of machines, you're going to preload these into your UTM. That's an infinite amount of input information for it, right? The input's supposed to be a finite string. The first finite string might give you the first machine, right? Two machines, fine, 2 finite strings. You're not allowed to have an infinite string. You can't give an infinite number of machines to UTM at the same time. Yes, concerned. This is a subtle point that's professional.
Could you generate the machine somehow and then you could do it?
Yes. You've got a very specific situation. You're now restricted in which machines you can run. If you did loaded one machine in and generated different versions of it, you could achieve that. We won't have reason to, but you could. But you can't get an infinite number of arbitrary different machines into your UTM at the same time. You can get 1, you can get 2, you can get 1 trillion, but you can't get an infinite number of machines. It's too much data to load. It couldn't hold an infinite number of windows at the same time. Getting those machines into your Turing machine is the problem. Okay?
I feel like a lot of things fall apart when we think of infinite.
As soon as something becomes infinite, that's right. So the point made, this was Toby's point, running an infinite number of input strings alone should seem like something you're concerned about. You have to be careful how you do it. So in this step, I'm going to tell you how to do it, assuming it's one machine running on all of sigma star, for instance. That's a useful thing to do. If you want to answer questions like the one that Yaya was concerned about, this is the starting point. Run it on all the strings in sigma star and see what happens with all of them. So this is something you actually might want to do. Here's how you do it. First of all, it has to be only a finite number of machines. It could be as many strings as you like, even infinite number of strings, not a problem. Machines still have to be a finite number of machines. Here's what you do. You load up the machine. You can spin up as many copies as you want. You load up the machine and run it for one step on your first string. Okay? After that, you load a second copy of the machine for the second input string, and you run them both for one step. And then you load a third copy of the machine and run them all for one step. And load the fourth copy of the machine, run them all for one step. The fifth copy of the machine, sixth copy of the machine. You can keep doing this forever. Here's the fact you need to realize. After enough steps, you will have opened up any given machine you wanted and run it for as many steps as you like. Right? I mean, the first machine is going to be ahead of the second machine, ahead of the third, ahead of the fourth, etc. But as you keep on opening more windows and running them all for one step, you'll eventually run the first machine for as many steps as you like. You'll eventually run the second machine for as many steps you like. You'll never have all of the infinite number of strings running at the same time, but you'll have more and more running at the same time. Yes. Oh.
So we're generating the input strings within the UTM, right?
Yes, so it might have a computation machine inside of it that generates the input strings for us.
You can't have a UTM that takes in one machine and an infinite number of input strings and run. You have to have some depth.
Yeah, you will have to be generating that's a very good point. You'll have to generate the input strings. If it's something simple, in fact, if it's any recursively enumerable set, you can make a set of strings. You can run your Turing machine on those. Most often, you're running it on one string or all of them. And those are both sets that work just fine. Yeah, good. And again, this is the key point. If you follow this, you cannot, just like we couldn't to run two machines, we couldn't run the first one till it quit and then run the second one till it quit. We have to share our time. You can share time with an arbitrary number of machines. Open up a window and run them all for one step. Open up another window, run them all for one step. Every window will eventually be opened. Every window will eventually be run for as many steps as you like. And because you never run out of memory, you can just keep on doing this, right? This is where the infinite memory is really important. Those are the only two things about time sharing you need to know. You can avoid the looping problem in a UTM by running things alternately. You can actually do things that in reality you as a human being couldn't. Theoretically, you could run a Turing machine on all of sigma star and check all of the results, at least all the ones that eventually terminate. The looping ones are just going to keep on looping. Okay, there's nothing preventing you from running a machine on all of sigma star now. That will be useful sometimes. This is our goal, is to actually to see what we can use Turing machines to show. And in fact, our main use for Turing machines, UTMs in this course, is that how they can be used to show facts about recursive sets, recursively enumerable sets. Some stuff that we thought should be true, we have till 3:30, right? 35 minutes, that's fantastic. Some things we thought should be true, we're actually in a position now to show, and I am super upset because I really need to write on the screen now. Let me hand out this problem set and you can start looking at it. It's effectively a problem set, but it's really just some class problems. We get through as many as we can, talk them through. Make sure you ask questions as they come up. But you can start thinking about them now. More important than writing them down is to think and ask questions. A fully complete version of this worksheet will be posted online as well. Okay, so more important than writing down stuff we say is to think about stuff we say and question it. Yeah, answer the question. So, first question. These are some facts, and for the exam, you should know these facts and also know how to justify them. None of them are very long. Say how you could use a UTM to justify these facts, and I want to make sure we're careful about when we need to use time sharing. Sometimes we do, sometimes we don't. I mentioned this before. The reason RE sets are called recursively enumerable is they're exactly the sets that an EM can spit out. Why are the sets generated by an enumeration machine RE? I said this in words before, and what I said in last class, and what I said is exactly what we're going to do with the UTM. How could you use a UTM to prove that a set generated by an enumeration machine is RE? Well, what's the point? A set generated by an enumeration machine, you might have some enumeration machine called E that generates it. To say a set's generated by an enumeration machine means there's an enumeration machine you could run to generate these strings. How do you show that a set is RE?
Make a Turing machine that will eventually say yes on every string.
Yeah. And it could loop or say no on the strings that aren't generated, which is going to have to. This is going to be a pure RE set in some sense. What would you do? Well, I'm going to use a UTM. My Turing machine to accept that set of strings is going to be a UTM. What will I do? I will load the machine E into memory. One of the things you could do on your web page, one of the things you can do in UTM, load in the particular enumeration machine that generates a set of strings, run it, and look at, well, I'll say look at, not gather, looking at each string generated. There's one thing I've skipped here. You should probably yell at me for this. My Turing machine is supposed to take a string and say yes or no. Okay, take a string, say X, as your input. A regular old Turing machine is supposed to take a string, accept or reject. So take the string you're looking for, X, take the EM, and start running the EM with that string X stored in your memory. Every string that E spits out, check to find the string X. If it ever spits out your string X, accept. That's the full description of what a Turing machine does that shows this statement. If a set's generated by an enumeration machine, encode that into a string theoretically. Run a UTM that does the following thing. It takes an input string from you, that's what TM does in the first place. It loads that enumeration machine into memory, and it runs it, and every time it spits out a string, it checks and sees if it's the string X that you were given. If it ever sees the EM spit out your string, you accept. I mentioned this last class. So this is exactly what I said to do last class, but now we have a UTM can actually do this, theoretically. What will happen if the string X is not generated by your enumeration machine? You run the enumeration machine, it's going to spit out string after string after string. If it doesn't spit out your string, what's going to happen in this program?
It's either going to loop or reject.
Well, it'll actually never reject. There's no reject. I never said to reject. It'll loop. This will loop on, simply go into an infinite loop. It'll keep on looking at strings and looking for X. Never finds them. It's going to loop.
Yeah, but is there not a way for us, because I know the string that I'm giving, right?
You know the string you're given. Yep, that's the input string for the UTM. Yep.
Yeah, so when it reaches that string.
If it reaches that string, you'll accept. So it can always say yes.
Okay.
But you'll never know that string's not eventually coming at you. So this is a pure yeah. Pass it over. This is a pure RE. This is the purest of an RE set. This algorithm will only accept or loop.
And then if you were to prove that, you'd have to take every string in a particular set and kind of run it as an input of.
Oh, be careful about this. To show a set is RE, all you need is a Turing machine. There it is. This is the thing you would do to say if a given string is in or not. Right? Take the input string, feed it to a UTM along with your enumeration machine, have the UTM run the enumeration machine, always checking every output for that X. Except this whole thing, put it in a box, right? This is the Turing machine that accepts the set E, but it only works one string at a time. That's a very good point. Yep. So to show a set's RE, you need a Turing machine that accepts each string of the set and doesn't accept the other ones. This definitely accepts every string eventually generated by the enumeration machine, and it definitely loops if it's not generated. This, by definition, accepts the set generated by E. So this justifies my usage of the terms. You'll see this typed up more neatly and perhaps not as sloppy in the solutions. But yeah, sets generated by enumeration machines. There is a way you with the UTM or the UTM by itself could run the enumeration machine on a given with a given target string in mind, and eventually answer yes if it's generated, and eventually not answer yes, in fact loop, if it's not.
This doesn't prove that sets generated by enumeration machines are not recursive.
It doesn't prove they're not recursive. Oh, absolutely. If you prove a set is recursively enumerable, that doesn't mean there's not a better way of answering the question that gives you the no's as well. So you will only get to prove that the set is recursively enumerable this way. There's a Turing machine that accepts the set that may loop. In fact, it always loops on any string not in the set. Yeah, great. Again, think about these carefully. We'll get through as many as we can. Oh, here's a fact we really thought was obvious. If you could answer yes in a finite number of steps and yes or answer no in a finite number of steps, you should get a set that's recursive. A set that's RE and co-RE together should be recursive. I said this, I said we can't quite justify it yet. A UTM is our tool to justify it. What was the problem justifying it? Being RE means there's a Turing machine accepting the set. Being co-RE means there's a different Turing machine accepting the complement. You've got two Turing machines. Well, UTMs can load two Turing machines at a time and run both of them. You have to use time sharing here. Be careful. A's RE and co-RE. So you've got some machine MA accepting A. That's the definition of RE. You've got a different machine MA bar accepting A bar. For A to be co-RE means a complement is RE. Means the Turing machine accepting a complement.
Shouldn't MA dash accepting A as well? Because we're saying that because A is co-RE, then it's...
Well, if A is co-RE, you'll see this happen a lot, so it'll become automatic. But if A is co-RE, there's a Turing machine accepting its complement.
Yeah. Okay. Yeah.
Yeah. So this is your given information if-then statement. Suppose the if, this is like math to CS200 now, right? Suppose that you have, to be RE, there is some Turing machine that accepts the set A. To be co-RE, there is some other Turing machine that accepts A bar. How are you going to show it's recursive? Find a recursive, what kind of Turing machine do you need? TTM, total Turing machine. How can I construct a total Turing machine that, given a string, will answer both yes, it's in the set, or no, it's not, and never loop? Well, you need time sharing. You're going to take an input string x, and you're going to kind of do these in pseudocode. Say what the UTM should do. Well, I'm going to load up both machines, and it's crucial. The real obstacle to explaining this was that there are two different machines. UTM doesn't care. It can bring up two windows, load two machines. What string do I want to run them on? I'm given a string x. I bring up my two machines. I run them both on x. One of them will definitely tell me yes if it's in. One of them will definitely tell me no if it's not. Run them on x one step at a time because one of them might loop. That's the time sharing part. Load them both up, MA and MA bar. MA will, if the string's in A, MA will eventually halt and accept it. If the string's not in A, MA bar will eventually halt and accept it. Yeah? Until one halts. Key fact, one of them has to halt. Your string is either in A or it's not. One of these machines is going to accept it. Okay? If MA halts, return, its result. I'll say accept accordingly. And of course, reject if it doesn't. So if the one that stops is MA, and accept will mean your string is in A, so you accept. An actual reject also, MA may also reject your string. If MA rejects your string, reject it. Basically, say whatever MA said.
It would have to be the other way around.
Yeah, if MA bar halts first, whichever one halts first is going to give you the answer. One of them is going to halt, right? You're going to reject if MA bar accepts, and accept if it rejects. Accept if not. You take two machines that half answer the question and run them alternating one step at a time. One of them halts, even if the other one loops. The one that halts will give you the correct answer. If MA halts, it's the one that accepts A, return what it tells you. If MA bar halts, it can tell the opposite of what you want to know, negate the answer and respond to that. This is the justification, needs a UTM. You need some way of running two machines. That's what this UTM thing does. Okay? One string at a time, given a string X, load these two machines, run X on them one step at a time. As soon as one of them halts, you've got your answer. A will give you the correct answer, MA will give you the correct answer, MA bar will give you the opposite of the answer you want. But either way, you will halt in a finite number of steps. Concerned?
I mean, not really quite, but like, I don't understand why you have to load both of them if you're just waiting for one to halt. Why can't you just use one?
Oh, great, good question. So here's the point. Suppose that these are both pure accept or loop machines, like we just saw. If I only loaded MA and just ran MA on my string, if my string's in A, that will halt and I'll accept. But if my string's not in A and my one machine keeps on running an infinite loop, I'll never know to reject. You're covering your both bases by running MA bar at the same time. If MA doesn't accept, even if it loops, MA bar will accept. So one of them has to halt. And that's the key thing. Neither one individually is guaranteed to give you an answer in a finite number of steps. But if you run them both, yeses and nos, one of them is going to halt. Even if the other one loops, that one tells you the answer. Yep. So think about the kind of machine we just saw in the last example. These could be just both that kind of machines. Accept or loop, accept or loop. One of them will eventually halt to accept, and then you'll have your answer. Other questions, concerns, Toby?
I know it's like existential, the MA and MA bar. Is it not possible? Like, isn't it impossible to verify that one machine is the complement of another machine in this case?
Well, no, it's not the complement of the other machine. The definition of a set, if I asked you, here's a set, why is it RE? You'd have to give me a Turing machine. Like, the way you justify a set being RE is to hand me a Turing machine. The definition of RE is there exists a Turing machine. So there's an existential bit. For you to even justify to me that your set's RE, somehow or other, you know that there's a Turing machine. And therefore you can encode it and feed it in.
Aren't there many sets where they could give you a Turing machine and you have no way of verifying that that Turing machine accepts that?
So this is the theoretical part. The only way you would know that a set was RE is if you had a Turing machine in your hand. Or you had some other rationale that told you there was a Turing machine, and that rationale should tell you it's a Turing machine. To be RE means that, by definition, means there's a Turing machine. How you would find it is not really the question. Why you would say the set's RE in the first place is because you have a Turing machine in your hand. The only way you could justify that first part of the if is to have a set with a Turing machine. So every RE set is going to come along with it a Turing machine. Every co-RE set is going to come with it a Turing machine for the complement, accepting the complement. Very good question. So this is similar to Yaya's question. The harder question is, given a set, find a Turing. That's a really ridiculously hard question. Question, Alex?
Is it possible for a string to reach the accept if not in the last, like if MA bar halts? Like,
all these are possible technically.
I don't think so.
Yeah.
Because aren't they opposite?
They're opposite, but even if these could both be total Turing machines.
Yeah.
They could. This is kind of Toby's question. One of them may finish before the other one does.
Okay, yeah, I see.
You have to handle all 4 cases because you know that at least one of them is going to finish. If they both finish, they'll both give correct answers, but you do have to run both of them and handle both cases. Yeah. Good. All right, great. So that's one more. I think about these carefully. We probably won't get to all of them. Oh, God, we got 15 minutes. We get a few more. We had that one. If A is both ARIA and A is recursive. Next question. Context-free sets are ARIA. I'm going to just talk through this one. So if you know a set's context-free, what do you know? This is Toby's question again. How would you justify that set's context-free?
There's an NPDA.
I'd rather not use an NPDA. I'd rather use the grammar. That was our principal def. There's a grammar that generates that set of strings. For a context-free set, there exists some grammar, some context. I'll say CFG to save some space and be correct. My God, I can't write. CFG generating it. Okay, let's say A is the context-free set. Do you have a finite time algorithm given a string? So I'm going to show this set's recursive. What do I need to show a set's recursive? Total Turing machine. I need to describe to you how to make a total Turing machine. It's going to take an input string X, and it needs to, in a finite amount of time, tell me yes or no it's generated by the grammar. Well, input the grammar. Call the grammar G. Do we have any algorithms to check if a string is generated by a grammar? Yeah, what was it? What do we need first, though? Chomsky. Well, that's algorithmic. Put G in Chomsky normal form. Technicality, what gets lost when you put a string in Chomsky normal form? Okay, careful about the empty string. When you're doing Chomsky normal form, you know at some point if empty string's accepted. If you were handed the empty string and you see the empty string was accepted, just accept and you're done, right? Otherwise, reject. So the empty string you will handle in step 2. Putting your grammar in Chomsky normal form will answer the question if the empty string is generated. Okay? If X is not the empty string, do CKY. That's a finite algorithm. Make your tableau, put your input string on it, fill in all the non-terminals and see if there's a nest at the beginning. After a cubic number of steps, you will know finite number of steps all that matters. So a finite number of steps, you will be able to answer yes or no to that question. Okay? Except if, S is in the lower left, reject. If not, that will give you an accept or reject after a finite number of steps. Chomsky normal form, you could execute in your laptop, in your Turing machine, in your UTM. But by the way, all of this is via a UTM, right? Whenever you're taking a Turing machine or something and doing stuff, talking about a UTM. You could write a program that inputs a grammar in some format. You could write an algorithm, put it in Chomsky normal form, and check if it has the empty string or not. You could write a little routine that does CKY. That will, for any string input in a finite number of steps, give you a yes or no. It's a total Turing machine. This thing in the box is the Turing machine. In fact, this justifies a fact. Someone mentions our block 2 things, our context-free sets, are within that middle bubble of recursive sets. They're even simpler. Recursive sets are our simplest sets in block 3. Context-free sets are inside those. Every context-free set's recursive. All the regular sets are context-free. All the finite sets are regular. So we're extending our reach a bit further.
We still haven't showed why it's recursive.
Yeah, this is it though. So how do you show a set's recursive? You find a total Turing machine accepting the set. This is the pseudocode for that Turing machine. The fact that you know your set's context-free means you have a grammar. Input the grammar in to take a string you want to check if it's generated. This is the algorithm the Turing machine could execute to answer your question. This will accept every string in A and reject every string not in A. So this is the machine that shows it's recursive. This is the total Turing machine, what it does. Make sense?
I think it's just the rejective not that is like the important.
Yeah. You will, I mean, no matter what happens, input G will be a finite number of steps. Putting in Chomsky normal form is a finite procedure. Do CKY is a finite procedure. CKY will finish, and you'll get an answer either way.
Yeah, because it's like it has to be like either there's an S or there's not an S.
So CKY gives you the yes and the no's, which, as you saw in exam 2. Great. Trying to think if there's something we want to get to here, that I should skip any of these. Oops. Intersection union product of two RE sets. Your standard closure properties. I'm not going to go through these in detail because they might be more interesting. Oh, wait, what's left? Blah, blah, asterisk. I kind of want to do 7 first to make sure we get to it. Now we have 10 minutes, so maybe I'll talk about these briefly. How would you, I'm not going to write it down in words, how would you show the intersection of two RE sets was RE? A set A and a set B. If A's RE, what does that mean? Turing machine accepting A, MA. Maybe I should write this down, God. Turing machine MA accepting A, and a Turing machine MB accepting some set B. That's what it means to be recursively enumerable. How am I going to show the A intersect B is recursively enumerable? I want a Turing machine. I don't need it to be total. I just need a Turing machine. I'm not going to be able to get a total one. How's it going to run? Well, input some string X. How am I going to check if it's in A and in B? Well, I'm going to load up MA and MB. In fact, MA and MB might be preloaded into my UTM, hard-coded in before I start. Run them both. I'll say run MA on X. Now I'm going to make this really simple. Run MB on X. Whoops. Except if both accepted. This is sloppy as heck. This is really sloppy. But because it's an intersection, notice there's no asterisk on intersection. You don't need time sharing here. Because if MA loops, you never get to the third step, right? But if MA loops, what do you know about the string X? It's not in A, so it's not in the intersection. You're happy with loops. If MB loops, it's not in B, so you're happy. This happens to loop on the strings that aren't in A or B, aren't in both A and B, so it's okay. If you want to do the same thing for unions, you'd have a different situation. You'd have to run MA and MB alternatingly, and as soon as one of them accepts, you accept. Right, so you need time sharing for unions, but not for intersections, interestingly. Okay. Product, you have to be careful. I'll let you think about that, because I do want to get to this, this other rather interesting problem before we get out of here today. Oh, what about complements? How would you show, oh, go ahead.
Are we not doing products?
I'm not going to do products. You would have to take an input string. I'll tell you how, I don't know if I should let you think about this or not. I'm going to put the solutions up. I'm going to let you think about it. You have to do a little loop to see if it's in a product. For a string to be in a product, you have to see if it splits into two pieces. Find all the splittings into two halves, run one machine on one, the other machine on the other, and see.
It accepts one of these splits.
Yeah, if you can get accepts on both of them, then you're good. You have to use time sharing though, because those things could loop. Yes?
Like one possible split. Like once I find out a particular split.
If a particular split
accepts
and the other one accepts, you're done. That's right. Toby.
Can't you, like, alternatively, could you just encode the product as an enumeration machine and check the string against that every time, like the same thing? And then you wouldn't have to do the splits.
Oh God. I mean, you could. I think that's harder, but you could. Yeah. You could cleverly use enumeration machines if you wanted to. There's a key thing I want you to realize, though. There is something to be said about given a enumeration machine, the set it generates is RE. It is true, but you'd have to justify that given a RE set, you can make an enumeration machine for it. You can, but you have to be careful about how. It uses time sharing and it's very delicate. It might be easier to just find all the ways of splitting up your string into two pieces and feed them into these machines with time sharing. And you'll actually run all of the splits at once because you need to use time sharing. You need to run all of them before you finish. So empty string, one of them might loop, that's right. So you're gonna load all the possible splits, and for each split, run with time sharing all of these, MA on the first half, MB on the second half.
And once any of
If any of them accept, you accept.
Right, accept.
Yeah, it's like branching, but it's deterministic because we're just doing one at a time. That's right. What about complements? How would you show using a universal Turing machine if the complement of an RE set is RE?
If you prove that it's recursive, is the complement.
Well, you won't be able to prove the RE set's recursive. In fact, I may ask you, would you attempt to prove that the complement of an RE set was RE? No, it might not be. So yeah, there's no rule for complements because complements of RE sets might not be RE. They're co-RE by definition, but there's no reason it has to be RE. So there's no rule for complements, same as in block 2. Finally, asterisk, you have to take your string and find all the way to splitting the substring and run your machine on all of them with time sharing. It's a big mess, but you could do it. I want to get to, nope, this one. This is cute. An enumeration machine spits out strings, possibly repeated, possibly in no particular order. This is a cute fact about recursive sets. If a set's recursive, if and only if there's an enumeration machine that spits out the strings in order, by length and lexicographically the usual order. So this is kind of cute. It really ties down the RE and the recursive sets. RE sets are generated by any enumeration machine. Recursive sets are generated by a enumeration machine in order. There are two things to show here to be clear, because if and only if. I'm going to get that eventually. If and only if. If a set's recursive, I think you should be able to make a Turing machine that generates those strings in order. How would you do it? I'm not going to have time to write it down. Enumeration machine is going to go in a loop through all the strings in sigma star. For each string, run your total Turing machine on it, and if it accepts, spit it out. That will be an EM that spits them out in order. Slightly harder part, not that much harder. If you have an enumeration machine that spits out the strings of your set in order, you can make a total Turing machine that accepts that set.
Because you know, if there's only a finite number for each length of string.
Yeah.
So it knows like once it's gone past.
Once it's gone past. So you do just like you did in the other case. For any given input string, you run the EM on it and see if it pops up. Is that my string? Is that my string? Is that my string? But as soon as you see a string past your string in order, you know it's not going to come up. As soon as it gets past your string that you're looking for, you know it won't generate and you're able to say reject. So that's kind of cute. Let's leave it. I think we're mostly out of time today. I will put up online this page with sort of full explanations of all of these. We've at least talked through or written down most of them. Your homework for today is really, work on problems at 7, think about your Turing machines and stuff. But think through these problems and make sure you understand how UTMs do these things for you. I've asked you a large percentage of the possible things I could ask you to justify with a UTM. Study them, right? A, know the facts. B, know how to show them with the UTM. B prime, realize if you need time sharing or not. Those are the only topics for today. Get some good rest this weekend. Monday is our first example of a set that's provably RE but not recursive. There are some hairy bits to the proof, but the goal for Monday is basically to make sure you understand why that set is RE but not recursive. Question?
So pseudocode for UTMs is our new favorite way to prove things.
In fact, for the rest of the course, pseudocode is our tool. Yep. Everything we do from this point forward will be pseudocode. You have to make sure that the things you say to do in your pseudocode are things that a UTM can do, and we had a list today of the things they can do. Your main tools are input strings, load up Turing machines and run them on some strings, maybe through completion, maybe for a few steps at a time, maybe time sharing. That is your tool for all of today's material, and it'll be for the rest of the course how we're going to treat Turing machines. Pseudocode, and again, the key thing is make sure the things your pseudocode says to do are things that a UTM is able to do. And really, that's the stuff that you could in principle do on your laptop with the animation, if and only if. Other than the fact you can run a whole bunch of windows without running out of memory. Okay? Good, so UTMs hopefully don't feel too bad after today. These are your things to think about and be able to understand and do with UTMs. And you're seeing your new paradigm of pseudocode for describing what a UTM or what a Turing machine does. That's your new tool. All right? All right, we'll leave it there. Rest up. Again, Monday, heavy day. The hardest stuff of the course comes shortly thereafter. It might be Wednesday next week. Prepare yourselves. Get this stuff understood. Get used to describing Turing machines running in pseudocode, because that's what we're going to be doing. The hardest thing we'll do will be using that principle in a complicated situation. Totally doable, and you'll have plenty of time before the exam to absorb it. But prepare yourselves. Next week, we hit the single hardest topic of the entire course, in my view. So, it's called reduction. It's a way we will be able to show that a given set is more complicated than another given set.
That's next week.
That's next week. But it's still more than a week away from the next exam. You're gonna have a lot of time to absorb that, even more time than you had to absorb the pumping lemma. And it's gonna take some thinking. If you're lucky, you'll click immediately. I don't know many people for which it's clicked immediately. I'm gonna approach it via an analogy and several other things. And the hope is that with enough work, this will make sense, because it's going to seem opaque at first.
I know the final's like cumulative.
Yes.
Is it going to be like pretty heavily weighted towards the new stuff?
There's only maybe 3 days of new stuff since the third exam. The final exam will be kind of more big picture questions and logical relationships between the blocks and big facts. You won't be doing any ticky-tack stuff on exam 3, on the final exam, except for the stuff since the third exam. You won't do CKY. You won't convert to Chomsky normal form. You won't do state minimization. You won't actually, huh?
What are we doing then?
You're answering questions about, well, there's whatever happens after exam 3, I could ask full depth questions. Everything else has to be about big picture questions. Lots of logical questions about sets being recursively numeral recursive. You know, here is a union. Is a union of two RE sets RE? Is the complement of an RE set RE? You know,
The last question, Pat.
a lot of logical deductions and maybe some explanations. I'm asking you to explain some relationship between some blocks, but it's going to be more higher level, big picture questions about all the old material. I'm not going to re-examine you on CKY or something. Yeah. We'll talk about that much more once we get close to the final. For now, exam 3 is about the stuff we'll cover in 7 classes. You've seen 3 of them. Wait, is that right? Yeah, there's Monday, Wednesday, Monday, Wednesday. That's it. There are 4 more classes starting Monday's something. Next Wednesday is probably the hardest single thing you'll do this semester. So once you get over that hump, things will be better in some ways. They won't be quite as hard at any rate.
So is there any algorithms or like mechanical things that we're going to do with this block or no?
Algorithms.
Like CKY or...
Nope,
So it's
not
all
really.
just theoretical.
It's theoretical. We're going to be talking through it. It's a good question that came up, this pseudocode idea. We're going to be talking through things Turing machines can do and things they can't.